Hello and welcome to Data Science for Everyone. Today we're going to explore the second part of a two-part series on hypothesis testing using R. Before watching this video, I highly recommend watching my first video. The link is in the description. Let's get started. In the first video on hypothesis testing, we covered one-sample tests, unpaired and paired two-sample tests, and ANOVA tests. In this part, we'll cover the following topics: one and two sample proportion tests, chi-square tests of independence, chi-square test of goodness of fit, and non-parametric tests. Let's start with one sample proportion tests. The goal of proportion tests is to determine whether the proportion of successes in a population, usually denoted as P, is equal to some hypothesized value, usually denoted as P0. We use this test when we have one categorical variable with exactly two outcomes, like yes or no, or true or false. It is also important that the data comes from a simple random sample, meaning every member of the population had an equal chance of being selected. This helps ensure that the results are statistically valid. Let's look at an example. The coffee dataset contains a survey of 5,000 individuals with their preferences for tea or coffee, along with whether they live in an urban or rural setting. The dataset has three columns: person ID for each individual, their preferences for tea or coffee recorded in the preference column, and the region where they live in the region column. Let's say our question is, does 60% of the population prefer coffee over tea? We'll use one sample proportion test to answer this question. We'll first set up our hypothesis for this test. We are looking at whether the proportion of people who prefer coffee is different from 60%. Our null hypothesis, H0, states that the proportion of the population who prefer coffee is exactly 60%, or P equals to 0.6. The alternative hypothesis, HA, challenges that, suggesting that the true proportion is not equal to 60%, meaning it could be higher or lower. This is a two-tailed test because we're interested in detecting any difference from 60%, not just an increase or decrease. We have set our significance level alpha to 0.05, which means we're allowing 5% chance of rejecting the null hypothesis when it's actually true. Let's understand the elements involved in calculating the z-score for one sample proportion test. P0 is the hypothesized population proportion. The value we assume is true under null hypothesis. In our case, it is 0.6 or 60%. This is a known value because we define it as a part of the hypothesis test. P hat is the sample proportion, which we calculate from the data we have collected. This is a known value because we compute it from our sample. P is the true population proportion, the value we are ultimately trying to learn about. This is unknown, which is why we are doing the test in the first place, to make an inference about it. Just below, you'll see the z-score formula. The formula tells us how many standard deviation away our sample proportion P hat is from the hypothesized value P0, assuming the null hypothesis is true. The z-score helps us determine how extreme our sample result is and whether it is statistically significant. Let's see how to compute the z-score for one sample proportion test. First, we calculate the sample proportion. That's the percentage of people in our dataset who said that they prefer coffee. Then we set our hypothesized population proportion, which in this case is 60% or 0.6. This is the value we're testing against under the null hypothesis. Next, we determine the sample size, which is simply the number of observations in our dataset. The sample size is 5,000. We set the alpha or significance to 0.05. With these values, we compute the z-score. This measures how far our sample proportion is from the hypothesized proportion in terms of standard error. The z-score is computed as 2.3. Is this score significant? Let's calculate the p-value to find out. When we calculate a z-score, we can transform it into a p-value, which helps us decide whether to reject the null hypothesis. If we have a left-tail test where we are checking if the proportion is less than a certain value, we find the p-value by looking up the area to the left of the z-score on the standard normal curve. If it's a right-tail test, testing if the proportion is greater than the hypothesized value, we find the area to the right of the z-score. We do this by subtracting the cumulative probability from 1. For a two-tailed test like the one we are doing here, we care about the differences in both directions, higher and lower. So we find the area in both the tails of the distribution. Since normal distribution is symmetric, we can simply double the area in one tail using the positive z-score. Computing the p-value, we can see that it is less than 0.05, which is our significance level. That means that the result is statistically significant, and we have enough evidence to reject the null hypothesis. We conclude that the proportion of coffee drinkers are not equal to 60%. Now let's move on to two sample proportion tests. This time as well, we'll look at the coffee dataset and ask the following question. Is there a difference between the proportion of coffee drinkers in urban and rural regions? First, we set up the hypothesis for the two sample proportion test. The null hypothesis H0 says that there is no difference in the proportion of people who prefer coffee between urban and rural areas. In other words, both groups have the same coffee preference rate. Mathematically, we can state that the difference between the two proportions is 0. The alternative hypothesis HA is that there is a significant difference between two groups. That means the proportion of coffee preference in urban region is not equal to that in the rural regions. The difference is not 0. This is again a two-tailed test because we're checking for any difference in either direction. We have set our significance level or alpha to 0.05, meaning we're willing to accept a 5% chance of making a type 1 error. Here's how we compute the z-score. First, we start by counting how many people in each region prefer coffee and store it in the counts variable. Next, we calculate how many total people were surveyed in each region and how many of them specifically chose coffee. This gives us the raw counts we need to move forward. Using those counts, we compute the sample proportions, that is the percentage of people in each region who prefer coffee. We stored them in prop urban and prop rural variables. We then calculate what's called a pooled proportion. This combines the data from both the groups under the assumption that the null hypothesis is true, that there is no difference between the regions. With the pooled proportions, we compute the standard error, which tells us how much variations we might expect between the two groups just by chance. Finally, we calculate the z-score. Since this is a two-tailed test, we compute the p-value just as we did before. As we can see, the p-value is less than the significance level of 0.05, and as a result, we reject the null hypothesis and conclude that there's a significant difference between the proportion of coffee drinkers between the urban and rural populations. Now let's look at chi-square tests of independence. Just as ANOVA extends t-tests to more than two groups, chi-square tests of independence extend proportion tests to more than two groups. Let's begin by quickly revisiting the proportions test we conducted earlier. Our primary objective was to determine whether there's a significant difference between the proportion of coffee drinkers in urban versus rural settings. For this, we used the two proportion sample tests, which compares the proportion of successes, in this case coffee drinkers, between two independent groups, in this case the regions. The result of the test gave us a small p-value, much smaller than a typical 0.05 significance threshold. This suggested that the observed differences between urban and rural coffee drinkers were statistically significant. In other words, there is a strong evidence to suggest that region influences coffee preference. However, there is a limitation. As you will see, this test only addresses a specific question, namely comparing the proportion of coffee drinkers in two regions. There is more to the story, especially when you start thinking about relationships between multiple categorical variables. We need a more general test that can assess whether two categorical variables are associated. And that's where chi-square test of independence comes in. It will allow us to examine the overall relationship between categorical variables. For example, preference, whether people prefer coffee or tea, and region, whether they live in urban or rural areas. Let me introduce the chi-square test of independence. The chi-square test is used to determine whether two categorical variables are independent of each other, or if there is an association between them. The key question we are asking here is, are coffee preference and region independent of each other? Like all hypothesis tests, we set up the null and alternative hypothesis. Our null hypothesis H0 states that the two variables, preference and region, are independent of each other. That is, a person's coffee preference is not related to whether they live in an urban or rural setting. And the alternative hypothesis HA states that the two variables, preference and region, are dependent. This means that where a person lives does influence whether they have preference towards coffee. Before running the chi-square test, let's explore the data visually. To plot the data, we'll be using the proportional stacked bar plot to compare proportions across regions. We'll use ggplot2 and set x-axis as preference and y-axis as region. Finally, we call geom_bar and set the position to fill. This creates a proportional stacked bar chart where each bar shows the breakdown of categories within each region, and the height of each section represents the proportion. This type of plot makes it easy to compare proportions visually between groups, helping us quickly spot differences in behavior or preferences. To run the chi-square test of independence, we are using the chi-square.test function in base R to explore whether there's a relationship between coffee preferences and regions in the coffee dataset. First, we create a contingency table using the table function with preference and region columns. Then we pass in the contingency table to the chi-square test function and print the results using the tidy function from broom. The test returns a Pearson p-value of 2.29 into 10 to the power minus 10, which is smaller than the significant level of 0.05. That means the result is statistically significant. So we reject the null hypothesis and conclude that preferences for coffee is dependent on the region. We can run the same test by swapping the variables. In the resulting stacked bar plot with swapped variables, we notice that the splits within each bar are quite similar, meaning the regions doesn't change much across different levels of coffee and tea preference. When we run the chi-square test of independence with the variables swapped, the results are identical. This is because chi-square test is symmetric. It doesn't depend on the order of the variables. That's why we phrase our question as, are variables x and y independent, instead of is x independent from y. The focus is on whether there's an association between the two variables, not which one is causing the other. Because the chi-square test only checks for statistical dependence, not direction or causality. Also, something to note, we didn't consider the tails, and the chi-square independence method doesn't include an alternative argument. This is because the chi-square test statistic is calculated using the square of the observed and the expected counts, and since squared numbers are always non-negative, chi-square tests are typically right-tailed tests. We have used the chi-square test to compare proportions in two categorical variables. This time we'll use another variant of the chi-square test to compare a single categorical variable to a hypothesized distribution. This is the chi-square test for goodness of fit. The chi-square goodness of fit test is a statistical method used to assess whether the observed distribution of a categorical variable matches an expected distribution. It is commonly used in cases where you want to compare the observed frequencies from the data you collect to the expected frequencies, which are the theoretical predictions. Let's demonstrate by setting up a hypothesis. Let's say we're interested in whether the preference for coffee versus tea in a population is evenly distributed. We set up the hypothesis like so. The null hypothesis H0 states that the preference for coffee and tea are evenly split, meaning 50% prefer coffee and 50% prefer tea. The alternative hypothesis HA states that the preference for coffee and tea are not evenly split. We also set the significance level or alpha to 0.05. To compute chi-square test statistic, first we set up a data frame representing our hypothesized proportions. In this case, assuming that 50% of the people prefer coffee and 50% prefer tea. We then calculate the expected counts by multiplying those proportions by the total number of responses in our dataset. Next, we compute the observed counts. That is, how many people in our data actually chose tea or coffee. We make sure to align the categories with our hypothesis, filling in any missing ones with zeros. The chi-square test statistic then measures how far these observed counts are from what we expected, category by category. The greater the difference, the larger the statistic, and the more evidence we have that the actual preferences don't match the hypothesized ones. Now that we have our observed and expected counts, we use the chi-square test using the chi-square test function from base R to compute the chi-square statistic and p-value. The chi-square statistic tells us how far off the observed values are from the expected ones, based on our hypothesis. After running the test, we see that the p-value is less than 0.05, which is our chosen significance level. This means the difference between the observed and the expected values are statistically different. So we reject the null hypothesis and conclude that the preferences for coffee and tea in our sample are not evenly split. There is a strong evidence that the actual preferences differ from a 50-50 distribution. Now we have come to the last part of this video where we will be looking at non-parametric tests. Each hypothesis test we have seen so far makes assumptions about the data. So what are these assumptions? Before we trust the results of our hypothesis test, we need to make sure some key assumptions are met. First, randomness. The sample should be randomly selected from the population. If it is not, our results might not generalize. We need to understand how the data was collected to assess this. Second, independence. Each observation should be independent of the others. This usually means that one person's response should not influence another's. Again, this depends on how the data was gathered. Third, large sample size. The test relies on a sufficiently large sample to approximate the normal distribution and ensure valid results. If the sample is too small, the test can become unreliable. If these assumptions aren't met, we risk drawing conclusions from a sample that doesn't reflect the population, making more false positives and false negatives, and getting wider confidence intervals, which means that more uncertainty in our estimates. So, checking these assumptions isn't just a formality. It is essential for ensuring the validity of our statistical conclusions. Here is a list of different tests with their ideal sample sizes. Notice that some tests like t-tests call for large sample sizes, over 30 observations in each group, and others like chi-square tests are more forgiving, requiring only 5 successes and 5 failures in each group. Visual inspection of the histogram of the data is usually reliable for judging normality. However, if you are in doubt, one of the methods to test if the data is normally distributed is called the Shapiro test. The null hypothesis of the Shapiro test states that the sample distribution is normal. If the test is significant, the distribution is not normal. Let's demonstrate the Shapiro test on a demo data. We have generated a numeric vector using the rnorm function by setting the mean to 0 and standard deviation to 1. We use the Shapiro.test function from base R to run the Shapiro test. We can see that the test yields a p-value of 0.9, which is higher than our chosen significance value of 0.05. Therefore, as expected, we conclude that the data is normally distributed. If the data was not normally distributed, the p-value would have been smaller than the alpha or the significance level, in which case we would have to use a non-parametric statistical test for any hypothesis testing on this data. Let's walk through a non-parametric test called the Wilcoxon-Mann-Whitney test, which is used when we want to compare between two independent groups. This test is equivalent to the unpaired t-test, except the Wilcoxon-Mann-Whitney test is run on non-parametric datasets. We are using the salaries of data scientists working at large companies versus those working at medium companies. We start by loading our dataset and filtering it to include only data scientists. Then we split their salaries into two groups based on the company size, large and medium. We use the Wilcox test function in base R. We are testing with the alternative hypothesis that salaries at large companies are greater than those at medium companies. Looking at the output, we can see that the p-value is approximately 0.99, which is much greater than our typical alpha threshold of 0.05. This means we fail to reject the null hypothesis. The Wilcoxon test is equivalent to the paired t-test and is used for non-parametric datasets. Here we are testing the hypothesis that salaries in 2025 are greater than they were in 2015 using the Wilcox test function in base R. Since we are comparing paired data, we must set the argument paired equals to true. As we can see, the p-value is extremely small, effectively 0, and certainly much less than our alpha level of 0.05. This means we reject the null hypothesis and conclude that salaries in 2025 are significantly higher than those in 2015. The Kruskal-Wallis test is equivalent to ANOVA and is used for non-parametric datasets. In this case, we are analyzing the salary differences across 4 experience levels. To run the Kruskal test, we use the Kruskal.test function from base R. Looking at the results, we can see that the p-value is extremely small and well below our alpha threshold of 0.005. Because the p-value is less than alpha, we reject the null hypothesis. This tells us that at least 2 of the experience levels have significantly different compensation levels. With that, we come to an end of the video series on hypothesis testing in R. If you have liked this video, please subscribe to my channel. I plan to bring new videos every week. Also, please like the video if you have learned from it and comment on what else you want me to cover. Thank you and happy coding!